Hi students, welcome back to my channel SADHIK Physics. So we are dealing with the wave optics now. We already discussed introduction to the wave optics now, interference, Huygens wave theory and YDSC Young's double slit experiment theory and Young's double slit experiment based on the numericals now. So in the previous videos we already discussed now, and in this video so we are going to discuss one important concept now, that is about diffraction, right? So diffraction, you can see here, interference and diffraction no can be observed for a wave nature only. So it can be observed for sound waves and it can be observed for light waves. No? Clear? So especially the diffraction, no? Diffraction, if it is want to take place, the diffraction, no? So diffraction means what actually? Diffraction means is nothing but a bending of a light ray. You might have seen so many times in situation, no, in our day-to-day life activities. No, suppose we are talking in a room. Suppose one person is standing backside of the door. So even though small gap is there, no, therefore he can able to hear the voice. Even the sound waves or waves, no, it will travel in a rectilinear propagation. So it will travel in a straight line in all the directions, no. But when it falls on an obstacle or on one edge, so therefore it will undergoes like a bending, no. Understand, no? So this bending phenomenon, bending of a wave at an obstacle, no. So we'll call it as like a diffraction. We can see the diffraction mostly in sound waves, no, because wavelength of sound wave is slightly larger. So in our numerical, that is the gaps and all this, and also it will be in centimeters or millimeters. So therefore there what we can write it, no, there we can observe the diffraction phenomenon very easily in the sound waves, right? But in light waves, therefore the wavelength of a light is very small. So therefore this diffraction phenomenon in the light, no, therefore to observe it is slightly difficult. Why? Because we should have the obstacle in the size of in the order of the size of the wavelength, no. Therefore how much wavelength is there, in that order only the obstacle should be there, no, right? So we'll see first of all bending, what is the diffraction, no. So why this is how this diffraction was explained by the Huygens, no, we'll see now. Suppose there is a obstacle is there, no, this is an obstacle. So therefore what happens now, here there is a sound is traveling now, or there is a wave is traveling, a plane wavefront is coming and falling now, or plane wavefront or any spherical wavefront, whatever may be that, no. So the wavefront is coming and falling on this one, no, due to this obstacle. So therefore suppose if it is light is coming, no, therefore this is a wall or a screen, this is a screen. So definitely light is traveling in a straight line, no, therefore the light, therefore above this one, no, like a light should be seen. So below this one, no, should be like a completely dark, that is nothing but a shadow. Clear? So we have to observe this one, no. But really if there is a light is coming here, no, you cannot see like even though rectilinear propagation is straight line, no. So here till here light should fall, no, here the completely dark should be there, no, but you'll see that you will not see the sharp dark shadow from here. So at this point, no, therefore here you are from here onwards you are able to see the dark shadow, and this region will be slightly light, it will be there. So it tells that when it is a light is falling at this point, no, therefore it will undergo like suffers a bending onto this one. Clear? So this bending of a light ray, so only you can call it as like a diffraction, no. So how this was explained by the Huygens, no. Huygens again they say that at every point, no, it will act like some secondary source, no. The secondary source is that it will be creating like the wavelet, therefore it is able to create like a bending of this one. Clear? So and the wavelength and size of the obstacle should be in the same order, therefore wavelength and so size of obstacle CLE obstacle should be in the same size, same order, no? I mean the same near to that one, no? Then only you can observe the diffraction. Clear? So here there are two types of diffractions are there. One is Fresnel diffraction, one is Fraunhofer diffraction, no? So what is Fresnel diffraction, no? Fresnel diffraction dealing is very slightly difficult, no? So Fresnel diffraction, so Fresnel diffraction, what it will tells now, therefore it will uses only the spherical wavefronts, no? Spherical wavefronts. So therefore here that means the source and the screen should be at finite distance now, right? So it's known distance only. So when it's very near the point source is there, therefore a spherical wavefront, no, it is going to get it now. Therefore here a source of light and the screen, so both are at finite distance now, finite distance. And handling with the spherical wavefronts, no, slightly difficult, no, we know it already. So Huygens mostly suggested to go for a plane wavefronts because it is we can deal with it easily. So Fraunhofer diffraction, no. So Fraunhofer diffraction. So what is this Fraunhofer diffraction now? So we are going to use in this Fraunhofer diffraction, no, we can use it like a plane wavefronts. Plane wavefront means what? Definitely plane means compulsory object. Screen should be at infinity and so source also should be at infinity. So source and the screen, no, therefore source and the screen are at infinite distance. I cannot go for infinity, no, therefore for this purpose, no, we are going to use like a lenses, right? So convex lens we are going to use this diffraction pattern, no. Clear? So in Fresnel diffraction, no, we are not going to use any lenses, no, because it's a finite distance, no. Infinite distance I cannot go on it, no. Therefore here for this one, no, we are going to use the lenses. Correct? So to see this diffraction phenomenon, no, therefore for the light, no, one simple experiment is there. So therefore you can take it as like a two razor blades, no, two blades you can take it, no, these two blades, no. So like this. So because the edges should be very sharp, no, therefore keep it very contact onto this, so that in this between this one, no, small gap will be there. With that one, no, be carefully. So with that one, no, you try to see the one bulb. So therefore what you are going to see it now, therefore you will be seeing like some fringes, no, some central one, no, it will be slightly more bright fringe will be there, then afterwards dark fringe will be there, then afterwards bright fringe will be there. You try to observe at home, no, therefore but be careful, so it may cut to your skin, no. So be carefully handle it, no. So that you try to join it, no, then you can see that through the joining, no, you try to see the light, not sunlight, don't use it, no. So this bulb only you can see it, no, then you can able to see the diffraction phenomenon. There some central maxima will be there, then afterwards fringe pattern you are able to observe it now. Clear, no? So therefore why that fringe pattern is taken place, no, let us see, no. Therefore we are going to discuss here single slit diffraction, no. Single slit diffraction, Fraunhofer diffraction, single slit diffraction, no, we are going to discuss here now. So can anybody tell me what is the difference between the interference and diffraction, no, right? So we'll see after this discussions, no, you will only understand that what is the difference between actually the difference between the diffraction and interference, no. So therefore if you did not see the interference, no, please watch it, then you can understand this concept very clearly. So now here what you are going to do, no, therefore we are going to take it as one single slit, no, one slit should be very smaller, no. So here one a plane wavefront is coming and falling here, no. So therefore here you are able to see on the screen, no. So this is the screen, this slit size is smaller, no. So this screen is at a distance is d, so this slit size is small a. Then you try to observe this, no, most of the right, this light rays is coming, therefore here there will be slightly large region, no, it will be there here, no. So this is your central maxima, so this central maxima, okay, so this is, you can call it as like a central maxima. That means more amount of light it will come and fall onto this one, no. So right, so maximum amount of light it is going to come and fall at this point, no. Clear? So this one, no. So after that one, no, therefore again there will be a dark band will be there again. So around this one, no, again you are going to see like a one more, therefore the maxima region it will be there onto this. This is one more maxima. So this we can call it as like a, so therefore first maxima. And then afterwards again you are going to see it, no, therefore here there is a one more pattern you are able to see it now. Therefore, this you can call it as second maxima. Second maxima. Therefore, in middle of this one now, in the middle of this, therefore here this region now, this is called first minima. Minima means what? Therefore, intensity is very very low. Therefore, so this is nothing but a second minima. So this type of pattern you are going to observe on the screen onto this due to the single slit onto this. Clear? So why this minima and maxima it is formed? No. Therefore, how to calculate? Therefore, this maxima and minima positions, all this one. No. Therefore, exactly how we did for interference. No. Here also you have to calculate the path difference. No. Right. So due to calculating the path difference, you can calculate the first minima, second minima, the width of the central maxima, all this one. So, but if you try to see the therefore intensity distribution, no, at the central maxima, therefore intensity is very larger. So then afterwards this is your first minima, then afterwards again second, therefore the intensity distribution it will be like this. But in interference, no, what you can understand, no, therefore all intensity, therefore all bright bands are, it will be in the same in size or same intensity. So all fringes are equal in size, no, but here it not like that, no. Therefore more total light, no, it is going to concentrate, it is a central point, no. So therefore this is nothing but like a central maxima. This is nothing but a first minima. First minima. So this is nothing but a first minima. And this is first maxima, second minima, second minima. So most of the times now we will calculate the first minima only. Why? Because we want to calculate the central maxima. So how much amount of spread is taken place, no? So this variation in how much is taken place, no? To calculate this one now we will go for mostly the first minima calculation only. So if I want to see this pattern, no, everywhere we cannot see this pattern. So therefore here the wavelength of the light which is coming and the size of the aperture, so it will be in the order of it is both, it will be the nearly to the same, nearly in the order, no. Therefore then only you can able to see this type of pattern. So wavelength of the light is very very smaller, no. That's why to see this one, no, slightly difficult in our day to day life, no. But for sound waves, no, therefore the wavelength is larger, therefore this slightly larger numerical aperture also, therefore sound wave will be spread it, no. Therefore the person who are behind the wall also, they can able to listen the sound which are produced in the wall. Clear? So therefore here now you can understand, therefore mostly this minima maxima it is formed, no. So this is formed is because of due to the again superposition of these waves. Superposition of these waves. So then you can understand that the difference between the interference and diffraction, actually both are same only. In mathematical way it will be the same. So it is also superposition only, that is also superposition. But here the difference is what? There two slits are we are going to use now. Here single slit we are going to use. Again there fringes are same size, no. Here the central maxima is more intense and more wider, so compared to the minima and maxima. Therefore this intensity distribution is wrong, it is not correct one, no. So not the same as your interference, no, right. So these are the slightly difference, no, but mathematically therefore these are nothing but a superposition of the waves, no. Right. So again superposition, no, therefore again how the minima is created, no, how the maxima is created. So where the minima is created, where the maxima is created, and what will be the size of the central maxima, angular fringe width, angular central maxima, these are the things, no, we will study one by one now, right. So for this one, no, therefore, so here for this one, no, to understand this, what I am going to do now, I am going to make this slit is slightly bigger, no, therefore to understand very clearly. Therefore this slit size is A. So therefore here now what I am going to do now, I am going to therefore divide this one into two parts. So therefore through this one now the wave is coming now, from one wave is coming here now, and through this one now one more wave is coming. This is the midpoint now, we are divided into two parts. This distance it will become like A by 2. Clear? And therefore these two are going to superimpose, no. Therefore here there is a therefore again there is a path difference, it will be created, no. So this path difference can be calculated as from this one, no. So but here this wave and this wave are they undergo like a in destructive interference like that, no. Therefore, to minima means compulsory path difference should be equal to lambda by 2. So, therefore, this path difference, no, therefore, you can write it as a by 2. So, into sin theta. So, therefore, it will be equal to lambda by 2. So, first divided by 2, therefore, it will be lambda by 2. A sin theta is equals to lambda. So, this is the condition for first minima. First minima. So, this is your path reference, no. Path reference is nothing but a lambda. Therefore, there is a condition for first minima. Now, we are divided into two parts, no. Therefore, first minima is created, no. Suppose if we are going to divide, therefore, actually we can remember that. So, if it is even number, it is there, no, even number. So, therefore, it is going to create like a minima. So, if it is divided into odd number, if you are divided into odd number, therefore, it will going to create like a maxima. Clear? So, first even number is what at 2, therefore, first minima. Again, therefore, next even number is nothing but a by 4 into sin theta is equals to lambda by 2. Minima condition is lambda by 2 only. So, therefore, you can write it as a sin theta is equals to 2 lambda. That implies this is nothing but a condition for second minima. Clear? So, therefore, here first minima, second minima, therefore, you can write down nth minima, you can calculate, nth minima can be calculated as, so a sin theta is equals to n lambda. Don't confuse here, no, for diffraction and interference, no. So, here a sin theta is equals to n lambda is the condition for nth minima. Clear? So, two parts we are dividing, first minima, 4 parts we are dividing, therefore, a by 4, because 4 parts we are dividing. So, therefore, here it is going to nullify, that is nothing but a 2 lambda. Clear? Clear? So, therefore, suppose if you are divided into odd number, therefore, if you are divided into 3 parts, so this area will become like a by right. So, first part, therefore, a by a sin theta is equals to lambda by therefore, lambda by 2. So, 3 parts, no, therefore, here you can write it as 3 parts, no, a by 3. So, a by 3 into sin theta is equal to lambda by 2, therefore, you will get it now. So, here, so for maxima, so what you can write it now, a sin theta is equals to lambda by 2, this is your first maxima. So, therefore, a sin theta is equals to 3 lambda by 2. So, this is for second maxima, this is nothing but a first maxima. Clear? So, therefore, what you can write it now, therefore, a sin theta is equals to 2n plus 1 into lambda by 2. So, this is the condition for nth maxima. Clear? So, where n starts from 0, 1, 2, 3. Here n value is equals to 0. So, therefore, it is nothing but a central maxima. Clear? So, this is your odd number, no, odd number. So, therefore, 1, 3. So, therefore, n starts from, so, 0, 1, 2, 3, so on. Clear? So, these are the conditions, no, again. So, again this path difference, no, can be calculated as, therefore, here, no. So, this is your, this also theta, therefore, this is d. So, this is y position, no. Therefore, tan theta is equals to y by d. So, thetas are smaller, no. Therefore, in the place of sin theta, I can substitute here, no, this one. Clear? So, therefore, here, so what is the positions of minimas? So, this is very important, no. Positions of minimas. So, therefore, you can write it as a sin theta is equals to, therefore, n lambda. So, a sin theta we can write it as a into sin theta is nothing but a y by d. So, is equals to n lambda, y is equals to n into lambda d by a. So, this is the position of our minimas. Clear? So, therefore, this is your first minima. First minima is nothing but a d by a. So second minima, therefore 2 lambda d by a, so on. These are the minima conditions now. Minima conditions. Clear? So what are the positions of the maxima? Positions of maximas. So therefore you know that a sin theta is equals to 2n plus 1 into lambda by 2. Clear? So positions of the maximas. So a into, therefore y by d is equals to 2n plus 1 into lambda by 2. So y is equals to, so 2n plus 1 by 2 into lambda d by a. So these are the positions of our maxima. Clear? So therefore here first maxima, these are the maximas. First maxima, therefore here 1, so therefore 3 by 2 d lambda by a. So second maxima 5 d lambda by 2a, so on. Clear? So these are the maxima conditions, these are the minima conditions. No? Now we want to calculate very important one now, very important, that is linear width of the central maxima. Therefore this is your so this is your central maxima, therefore here linear width. No? So therefore linear width, what you can write it down, this distance is nothing but a first y minima, this is y minima. Clear? So therefore here linear width of central maxima. Clear? So that is nothing but a 2y1. 2y1 is nothing but a first minima to first minima. So therefore 2 into d lambda by a. So will be the linear width of our central maxima. Clear? Now they may ask you angular width of the central maxima. What is the angular width? No? So first let us go for first this angular width. No? Therefore here we can rewrite it as, this is nothing but a angular width of central maxima. What is the angular width of the central maxima? That is nothing but a 2 theta. So you know that a sin theta is equals to lambda. So theta is equals to lambda by a. So therefore 2 into lambda by a. Clear? So therefore this it will be the angular width of the central maxima. So these are slightly important, no? Very important. So linear width and angular width, no? So for our diffraction. No? Clear? Now we will see some questions. No? Go through these formulas. This is your first minima, second minima, first maxima, second maxima. So these all are the concepts. No? These all are angular width and linear width. No? We will see some questions now. Clear? Let us see here. No? This question. Right, light of wavelength, here the wavelength is given, no? How much now? 6000 Armstrong, that is nothing but a 6 into 10 the power of minus 7 meters, 10, therefore 3 concept. Is incident normally in a slit of width, no? Therefore slit width is given as how much, no? 0.3 mm, so 3 into 10 the power of minus 4 meters. Calculate the distance of first minima on a screen placed at a distance of 8 meters. Therefore, capital D is equals to 8 meters. So, distance of first minimum, calculate the distance of first minima on the screen placed. So, first minima from the center of the central maxima, you can write it now. So, this is nothing but y1 is the distance of a first minima from where, no? From the center of the central maxima, no? So, therefore, it is nothing but a d lambda by a. So we can rewrite it as d is nothing but 8 into lambda is nothing but 6 into 10 the power of minus 7 divided by 3 into 10 the power of minus 4. 3 ones are 3 twos are, therefore 16 into 10 to the power of minus 3. So 16 millimeter will be the distance of our first minima from where, no? From the center of the central maxima. No? Clear? Now we will go for one more question. right. So a slit width of there is a slit width is there, no. So that is nothing but a is equals to 2 lambda and the distance of the screen is d, okay, d. So what is the angular position of the first minima? Angular position of the first minima. So this is here center of our central maxima. So therefore he is asking angular position of your, this is your first minima. Clear? So therefore here what you can write it now, sin theta is equals to lambda by a. So r, this distance we know it now. What is this distance now? This distance is nothing but a y1. So y1 is nothing but a lambda into d by a. So therefore we can write down d, no. Therefore tan theta so is equals to y1 by d. So y1 is nothing but a lambda d by a by d into a. Therefore get cancel out, no. Lambda by a. So what you can write it now? Lambda by a. So this I can write down, okay. So anyway you can get the same value. So sin theta so is equals to lambda by 2 lambda. So therefore it get cancel out, no. 1 by 2. 1 by 2 is nothing but how much now? Sin 30. So sin 30. Therefore theta is equals to 30 degree will be your angular position of the first minima. Linear position of your first minima. Therefore linear position is nothing but a, so lambda into d by 2 lambda get cancel out, no. Therefore d by 2 so will be your linear position of our first minima. Clear? So now let us go for one more question. Right. So here red color light of our wavelength. So wavelength is given as how much now? 6000 angstroms, can be written as 6 into 10 the power of minus 7 meters. At a distance of the source falls on a slit of, so there is a slit is there, no. Therefore so 0.75 mm, 0.75 into 10 the power of minus 3 meters. What is the distance between the first two dark bands on each side of the central bright of our diffraction pattern observed on a screen? So therefore d is kept at 1.5 meters. Clear? So he is asking first two dark bands. First two dark bands is what? Therefore here there will be a this is your central maxima. So therefore this is your first minima, first maxima, second minima, second minima. He is asking this distance, therefore y distance now. So from the center now, what you can write it now? This is nothing but a y1 and this is y2. So this distance is y2 and y2. So therefore it is nothing but a 2 into y2. Clear? So therefore here distance between these are now 2 into y2, therefore 2 into, so y2 is nothing but a 2d lambda by a. So that is nothing but a 4d lambda by a. 4 into d is nothing but a 1.5 into 6 into 10 the power of minus 7 divided by 0.75. So 0.75 into 10 the power of minus 3. So what I can rewrite it as now, therefore here, so this is here, okay, I'll take it top now. So this simplify it, no. 0.75 I can rewrite it as 3 by 4. Right. So therefore here 4 into, so 3 by 2 I can write down, 6 into 10 the power of minus 4 by 2, 3 by 2, this is 3 by 4. Clear? So this taken here. So 3 cancel here now, 4. Therefore here it will be the 2. So 12 into 4, 48 into 10 the power of minus 4. So therefore here 48 into 10 to the power minus 4, that is nothing but a 4.8 millimeter. So will be the distance. Clear? So then let us go for one more question now. If central fringe width is about 3 millimeter, therefore, so linear is nothing but a 2d lambda by a, so therefore it is nothing but a 3 millimeter 10 to the power of minus 3. Wavelength is given as 600 nanometer. What is the slit width? If the screen is at, this is d, this is a wavelength. So therefore here 2 into d is given as how much now? D is nothing but a 30 into 10 to the power of minus 2, wavelength is nothing but 600 into 10 to the power of minus 9 divided by A is equals to 3 into 10 to the power of minus 3. A is equals to, therefore here, so this is 60 into 600 into 10 to the power of minus 11, so divided by 3 into 10 to the power of minus 3, so this is now. So what I can write it down, this is 3, so therefore it is 20. So this is taken 6 now, therefore 12 into 10 to the power of 6 minus 11. So 12 into 10 to the power of minus 5. So therefore 3 taken now, 0.12 millimeter will be your size. Clear? Now let us go for one more question. Right. So if the central width is about 2 centimeter in a single slit diffraction, central width is nothing but L is equals to 2d lambda by A is nothing but 2 into 10 to the power of minus 2. In a single slit diffraction of slit width is this one, no? This, what is the distance of the screen? Wavelength is given. No? D is, we have to calculate. D is equals to, these 2 cancel here, no? D is equals to 10 to the power of minus 2 into A by lambda, therefore 10 to the power of minus 2. A value is nothing but 0.3 into 10 to the power of minus 3 by wavelength is nothing but 600 into 10 to the power of minus 9. Clear? So therefore here 3, so this is 0, I can take it as no, therefore here 3, I can add 0 here now. Therefore, so 3 ones are 3, 2000, clear? So this is 10 to the power of minus 6 no, therefore 1 by 2 into 10 to the power of minus 5. So this is minus 6 no, plus 6. So how much it will be now? Therefore it is 10, 10 by 2, that is nothing but 5 meters. Clear? Now we will go for another question. Light of wavelength, therefore there is a wavelength is given as how much now? 3000 angstroms, therefore 3 into 10 to the power of minus 7 meters. Incident normally on a slit width of is how much now? 15 into 10 to the power of minus 5 centimeter. Centimeter means 10 to the power of minus 2 meters. 15 into 10 to the power of minus 7 meters. Find out the angular width of the first secondary maxima. First maxima. Therefore, here this is your central maxima. So this is your maxima here now. So he is asking, this is your, this is theta. Clear? So this distance is how much now? This distance is nothing but a angular width. Therefore, this is nothing but a y2 maxima. Y2 is nothing but a 3d lambda by 2a. Clear? So this distance is given, no? Distance he did not give. D I don't know. So therefore here what I can rewrite it as no, therefore tan theta, it can written as therefore y2 by d, y2 is nothing but a 3d lambda by 2a into d, cancel here no. So 3 by 2 lambda by a, 3 by 2, lambda is nothing but a 3 into 10 the power of minus 7 by 15 into 10 the power of minus 7. 10 the power of minus 7 cancel now, 3 ones are 3 5s are. So 3 by 10, therefore tan theta is equals to, so 0.3 theta is equals to nearly 0.3 radians. So theta is smaller. Clear? Huh? Clear? So now we will go for another question. Now a linear aperture whose width is given, therefore A is given how much now? So meters, so therefore 4 into 10 the power of minus 4 meters. Immediately is placed immediately in front of a lens of focal length is 30 centimeter. No? The aperture is illuminated normally parallel beam, no? Therefore of wavelength. So therefore wavelength is given how much now? So 10 the power of minus 4 into 10 the power of minus 2 meters. So 10 the power of minus 6 meters. The distance of first dark fringe pattern observed from the center. No? Therefore does not matter, no? Focal length is given, therefore does not matter. Here plane wavefronts are coming, therefore. So here therefore here there is a, so what is asking now? Is asking the distance of first dark band of the diffraction pattern from the center of the screen. Therefore here, so this is your first dark band, no? Therefore the distance, linear distance only, it did not ask. Therefore this is your linear distance, no? So therefore d lambda by a. Clear? A linear aperture of width is given, no? Therefore the aperture is illuminated normally by the parallel beam of this one, no? Then see if it is normally means parallel beam is coming, means this nothing but d value should be equal to 30 centimeter 10 to the power of minus 2 meter. So therefore y1 will be equal to d 3 into 10 to the power of minus 1 into lambda, therefore 10 to the power of minus 6 by a, therefore 4 into 10 to the power of minus 4. So what I can get it now, therefore taken top, no? Therefore this is 2, so this is 3, therefore 3 by 4 millimeter distance. Clear? 3 by 4 means 0.75 millimeter. So therefore 0.075 centimeter. So will be your answer now. This should be your answer. Clear? Right? Let us see one more question now. Right. So let us read this one now. Double slit experiment, YDSC experiment now, right? Two slits are 2 millimeter apart now. Therefore here double slit experiment it is given now. Therefore here d is equals to 2 millimeter, 2 into 10 to the power of minus 3 meters apart. Therefore 2 slits are there. Therefore here these 2 slits are there now. So this is d. Clear? So therefore a screen is placed at a distance of 1 meter away. So d is equals to 1 meter. What should be the width of the each slit? Therefore he is asking this slit width. Therefore it is a. For obtaining 8 maximas of double slit, right. So it is obtaining 8 maximas of a double slit within the central maxima of single slit. So this line is very, very important. So therefore this line, understand this one now, obtaining 8 maximas of double slit, 8 maxima of double slit now, so which is to be within the central maxima of the single slit pattern as a same distance. A monochromatic light of wavelength is 500 mm. Okay, right. So here lot of information is there, no? Therefore here wavelength is given as how much, no? 500 nanometer. So 500 into 10 to the power of minus 7, 5 into 10 to the power of minus 7 meters. So this is, no? Therefore what it is says now, there is a linear width is there, no? Therefore this is a linear width, no? So this is a linear width, no? Therefore within this linear width, no? Therefore linear width is how much, no? L is equals to 2d lambda by A. So therefore that should be equal to 8 maximas, therefore 8 betas should get it, no? Clear? So therefore here that means actually diffraction pattern is nothing but it is like this only. Therefore this is your central maxima, no? Therefore within this one, no, there is a, I will drop this one, no? So we will discuss this. So here there is a this is your central maxima, it is there, no? This central maxima is nothing but is a composition of your this minimas. Therefore here this slit is divided, no? We are did the diffraction pattern, no? The slit is divided into number of parts, no? That all constitutes like a one complete maximum, right? So very simple one, no? See here, let us see this one, no? So here therefore 8 beta, 8 into fringe width is nothing but a, so lambda d by d is equals to therefore 2d lambda by A. So d lambda get cancel out, no? D lambda. So therefore this is nothing but a, this is 4. So therefore he is asking A is equals to d by 4. D by 4. So d by 4, d is how much, no? 2 into 10 to the power of minus 3 by 4. So it is 1 by 2, therefore 0.5. So 0.5 millimeter will be your size of the each slit. Clear? Right? So slightly, so different question. Now let us see one more question. Yeah, therefore this concept, no, actually now it is removed from our CBSE, but question is got, no? We will see that question. For what distance of a ray optics is good approximation, no? Where aperture is about 3 mm wide and wavelength of this one is given. Therefore good approximation means ray optics means what? Ray optics means what? Light is a ray. Light is nothing but a ray. There should not be any diffraction effect, should not be there. Clear? That means if a one slit is there, no, this is one slit is there, no. So therefore same light, no, it should be able to go it, no. After traveling some distance, no, therefore this is becoming wider and wider and wider and wider, right? So when it is becoming wider, no, therefore at that point, no, so the diffraction effect is there, therefore it is not traveling in a straight line, no. Therefore the minimum distance what you have to travel, no, therefore so that the slit size, no, should be equal to the same as this one, no. This is here same, this distance is d. So what you can write it now, therefore distance, this distance is d, and d I can rewrite it as like a z. So z up to what distance, no? Clear? So therefore this should be the central maxima, should be there, no? Therefore here, so what I can rewrite it as now, therefore here I can write it as therefore tan theta. So theta is smaller, no? Tan theta, so is nothing but a this is nothing but a, this is a by z. So but here sin theta can be written as lambda by a. So therefore this should be the lambda by a. So therefore z is equals to a square by lambda. This is here right distance for good approximation, no. So what you can write it now, aperture, no, 3 millimeter, 3 into 10 to the power of minus 3 whole square by wavelength is 500 nanometer, 500 into 10 to the power of minus 9. So this is 9 into 10 to the power of minus 6 divided by 5 into 10 to the power of minus 7, 5 into 10 to the power of 7. Clear? So therefore here it will be 9 into 10 divided by 5. 9 into 10 divided by 5. 5 ones are 5 twos are, therefore nearly 18 meters. So this is up to 18 meters, no, therefore light will not undergo any spreading of this one. Therefore, you might have seen ray optics now we did not go for 1 meter, 2 meter, 10 meter. Always we use 10 centimeter, 20 centimeter, 30 centimeter. No? So, because light is considered to be like a ray up to certain distance, no, therefore up to 18 meters. After 18 meters, no, therefore the diffraction pattern is going to be observed onto this. At that point, therefore light will not be in the form of like a ray. So, but up to 18 meters is a huge distance, no, therefore, so within that one, no, light is considered to be like a ray. So, therefore ray optics is very good, valid onto this. Clear? Right? So, now we will go for, okay, right? I think we discussed almost all concepts, no, right? So, regarding the diffraction. So, thank you for watching. Please subscribe to my channel now. So, those who want to learn the physics, no, so please share my videos, no, so that they can also learn physics very easily. Thank you.